So in order to make this a bit more concrete, let's look at an example, namely of a composed quantum system made out of two two-level systems. So we have a composed quantum system made out of two parts, and in each part we have two independent states that we are just going to label again with 0 and 1. But these are the states of the first part, and these are the states of the second part. Now in our quantum state for the composed system, we have to account for all the possible combinations of the states of these two different parts. And according to the superposition principle, the most general state would be a superposition of all of these. I introduce some coefficients, alpha, beta, gamma, and delta for these. So now we can actually group these also into a vector, and this would just be a vector of 4 components. Note that I ordered all the states so that we first increment the second entry as far as we can go, and then we increment the first entry. And then we again carry on with the second entry. Now this can also be thought of as a collection of two vectors. So let me make this very concrete, just like this. So you can also think of this as a collection of two vectors, and if you look at the meaning, the vector where we have the coefficients alpha and beta has the first state fixed in the state 0, and the vector with the coefficients gamma and delta has the first part of the system fixed in the state 1. So these are our states. So how does it work with the observables? Well, let's look at the observable x as an example. Now in Dirac notation, this is going to take the state 0 and convert it into the state 1 for just an individual quantum system for each of these two different two-level systems. So as a matrix, this corresponds to this matrix here. And if you multiply it to the state 1, 0, for example, you get 0, 1. So you start from the state that corresponds to your first basis vector, and it is going to be transformed into your second basis vector, just according to this rule. And the opposite also works out. Now let us work out what this does to our state psi when we either work on the first or the second part of our system, so one of our two-level systems. Well, let's look at this one first. So we want to apply this operator on the first system and use this rule here. So when we apply this to this part here, the 0 here of the first part of our quantum system should become a 1. And then this 0 here should also become a 1. But the state of the second two-level system always remains fixed because this is an observable or operator acting on the first system. Then we have the coefficient gamma, and now we have a 1 here, so that should become a 0 according to this rule. And finally also this one here becomes a 0. And what we end up with is a new state. And now we can again represent this as a vector. But now we have to take again the same ordering of the numbers. So we have to look at the entry in front of this very first placeholder number 0, 0 here, and this is a gamma. Then we have a delta in front of this 0, 1 here. Then we have an alpha, and then we have a beta. So therefore, in terms of matrices, this operator here should correspond to a matrix which transforms this vector into this vector. And we can indeed write this down in the following form. I write it down very explicitly. Now you see this looks very much like the matrix which I've written here, but with the different blocks replaced by the multiplication of an identity matrix. So if you multiply the 1 by an identity matrix, you just get the identity matrix. If you multiply the 0 by a 2 by 2 identity matrix, you just get a 2 by 2 block with zeros. And this is indeed the correct form, because when you work out what this does to this vector here, this is simply interchanging these two mini vectors. And this is indeed what is happening here when you start from this state and you want to go to this state. Now let's see whether this also nicely works out for the second operator. So now we act with this operator on the second part of the system. We can still apply the very same rules as given here, but we just have to look at the second entry here in these different basis states. So we get alpha times 0, and now the second 0 here becomes a 1 plus beta. Now the first entry will always remain fixed, so we get beta 0, 0, gamma 1, 1, so we have changed this 0 into a 1, and delta 1, 0. And again, we can interpret this as a vector just as here, when we just see what are the entries in front of these basis states in the correct order. So now we have a beta in front of the 0, 0, an alpha in front of the 0, 1, a gamma, a delta in front of the 1, 0, and a gamma in front of the 1, 1. Now when we want to express this in terms of a matrix multiplication, we need a matrix that is interchanging these two entries, so that alpha beta becomes beta alpha, and these two entries, so that gamma delta becomes delta gamma. And this is given by the following matrix. Given here. And you can simply check this by a matrix times vector multiplication. Now these 4x4 matrices are not too complicated, but as already mentioned when we introduced the general definitions, they can be written even more compactly by just making use of this block form here. And for x2 we can simply write it like this. Now the zeros are 2 by 2 blocks of zeros, just representing what we have here and here, as well as what we have here and here. And this matrix X is just the matrix that we have here. And the identity matrix are just the 2 by 2 identity matrices that we have at these places here. Now you can do the very same with the other Pauli matrices, and you just arrive at the same block form. So for instance, if you start from the Pauli matrix Y, then Y1 would simply be given by the following 4x4 matrix, where the zeros here again are 2 by 2 blocks, and Y2 is even simpler, just the Pauli Y matrix on the diagonals of these 2 by 2 blocks. And for the Pauli matrix Z, we start from this definition here, and then acting on the first part of our quantum system, we simply obtain this form here, and acting on the second part of the quantum system, we obtain this form. And so just for example, we can write this again as a 4x4 matrix by replacing these matrices here by the corresponding 2 by 2 matrices, and the zeros here by the corresponding 2 by 2 blocks. And so we can recover the full form of these 4x4 matrices always very simply. But even more, we can also do many of our calculations just in these block forms. So we don't even need to convert everything to these 4x4 matrices. So for instance, when we want to multiply this matrix x1 with a vector made out of these components alpha, beta, gamma, delta, then we can just group these into some symbols, say psi1 and psi2 into two mini-vectors. And then work out our matrix multiplication so that we obtain 0 times psi1 plus 1 times psi2, but these are now matrix times vector multiplications, but this does not really matter. So there we would just obtain psi2. And here we would obtain 1 times psi1 plus 0 times psi2, and this is just psi1. And this is indeed exactly the result which I mentioned above, because this corresponds to these two mini-vectors interchanged. So we can just write this as gamma delta, alpha, beta. So we can do a lot of our calculations simply using these block forms, and this will turn out to be very convenient. We can use these block forms even to determine the eigenstates and eigenvalues of these observables. So for instance, when we think of the observable Z, this has eigenvectors 1, 0 and 0, 1 with eigenvalues +1 and -1. And now the operator Z1 simply turns out to have eigenvectors phi 0 and 0, phi, where these are again these mini-vectors with two entries, and phi is sort of an arbitrary state of the second quantum system. And again, the eigenvalues turn out to be just plus and -1. And just to give a second example, for the operator x, we had eigenstates corresponding to the even and the odd superposition of these two quantum states. And if we now want to translate this into eigenstates in our composed system, we simply find the forms with these mini-vectors, phi and plus minus phi, so we have to use the same state for the second quantum system, but just put it here into these positions. And you can simply check that these are the correct eigenstates or eigenvectors by a matrix multiplication. And again, the eigenvalues would just be plus or minus both for the individual quantum system that we study here and for looking at this first part of the quantum system. And very similar constructions we can also carry out for the second quantum system. Now we could carry on and talk about the dynamics of this composed system, but this will indeed be a central part of the third chapter in this course when we lay down the general foundations of quantum information processing in terms of the most basic physical components and the way that we can manipulate them. So we will come back to this later. And when we then consider measurements, we can use our general postulates and use these eigenvectors. Now the fact that we have an arbitrary state here of the second quantum system means that we deal with degeneracy. And so if we wanted to calculate probabilities for observations of the first quantum system, in this case we would have to take this degeneracy into account. But in practice this is very easy. For instance, when we consider the observable Z of the first quantum system and ask if the value that we observe is 1, this corresponds to the first of our two quantum states, the one with the 0 entry. Then we just have to see where the 0 entry appears, and it appears in the state 0, 0 with a coefficient alpha, and in the state 0, 1 with a coefficient beta, and so we just have to add these two probabilities. And similar for the observation of the other value, the other eigenvalue, which is -1, we just get the other two amplitudes because they are in front of the basis states in which the first quantum system is in the state 1. And analogously, we can carry this out for the second part of the system. Now we just have to see where the second part of the quantum system is in the state 0. And this is in the state 0, 0, so with the amplitude alpha, and in the state 1, 0, where we have the amplitude gamma. And for the other possible outcome with an eigenvalue -1, we simply get the other two amplitudes, beta squared and delta squared. Nonetheless, something very interesting is hidden behind these probabilities, and this is what we are going to discuss next. In the remainder of this chapter, we are going to address two key questions. Namely, what can we learn about a quantum system when we have access to only a part of it? And how do the different parts of a quantum system influence each other? And in the answer and discussion, we will encounter two key concepts, that of a density matrix and entanglement. Density matrices are a more generalized notion of a quantum state, and they can be used, for instance, to describe just a part of a quantum system. And entanglement is a certain correlation between the states of different parts in the quantum system. Indeed, along with the superposition principle, entanglement is one of the key resources for quantum information processing. So next we are going to have a look at the density matrix, and then we are going to turn to entanglement.